Hello ladies and gentlemen, we're going to start our next chapter, 7.1, our exponential growth functions. The objectives are to graph and use our exponential functions. We're going to model some real life scenarios. Then we're going to learn about compound interest formulas and understand the difference between simple interest and compound interest. So that will make today's lecture a little bit longer. And then your homework problems are word problems, so it'll take me just a little bit longer to write it. So tonight's video would be a wee bit longer. All right, so a couple of things to remember. When we're talking about domain, remember that we are talking about the x values, so along the x-axis that makes a function work. And then if we're talking about range, the range is the y values that make a function work. All right? So we're going to introduce a new parent function. We've learned a few so far. But the new one that we're going to introduce today is called an exponential growth. Okay? All right. We use exponential growth a lot in science when we're talking about population growth, when we're talking about how bacteria multiply. So we use this a lot in science. We also use exponential growth when we talk about money, and primarily when we talk about an investment or credit card debt. All right, so for our parent function, it always crosses the y-axis at 0, 1, and our parent function is going to be written as a, b, and the x is in the exponent position. So notice that this is different than things that we've done in the past. In the past, the x would be down here as a base, but now the exponent is in the exponent position, so I'm going to say that the x is in the up position. Okay? In this particular case, you'll notice that this graph will never cross the x-axis. So this would be the equation where y is equal to 0, and that's actually going to be called a horizontal asymptote. And we'll do a lot with asymptotes in the next chapter. So for right now, I'm just going to tell you that this is a value that this graph is trying to get really close to, but will never actually cross. So that's by definition what an asymptote is. Okay, so it's going to try to get closer and closer and closer to that value, but it'll never quite get there. Okay, we can have vertical asymptotes, horizontal asymptotes, and slant asymptotes. Okay, so we would say that our parent function, a b to the x, has a horizontal asymptote at y is equal to 0. So in our generic formula, I'll write it again, a b to the x. A is going to be the initial value. Okay? So whatever I'm starting with, that's going to be my initial value. It's also the y-intercept. Okay? B is going to be the growth rate. And many times in your book they give you the growth rate, but if they don't, it would be 1 plus whatever the percentage is. And then x is going to represent time. And usually time is in years, but it can be a little bit different. Okay? All right. So now what we're going to do is talk about translating our base equation. So if you'll remember, an h means it is a horizontal translation. And k is a vertical translation. Right? So we've talked about those before. We've actually done lots of work with our horizontal and vertical translations. So now I'm going to show you what an equation would look like with those when it's in a new situation like this. So let's say I had the graph y is equal to 4 times 2 x minus 1, both of those are in the up position, and then minus 3. All right, so if I described my translations, I would say that this one has a vertical stretch of 4. I'm just going to write that the growth rate is 2. Okay? It's going to move 1 unit to the right. Remember that all horizontal translations are associated right with the x, and then all vertical translations are associated outside the function, so then it's going to shift 3 units up. Okay? Alrighty. If I graphed this function, okay, it would look something like this. So instead of my horizontal asymptote being here at y is equal to 0, now it's going to be down here at y is equal to a negative 3, because everything moves the same amount. So my intercept would move and my asymptote would move down 3 as well. Okay, so the graph, if I did this on my grapher, would look something like that. Okay, I will show you how to enter it in your grapher in a little while. The domain for this particular graph is all real numbers because there's no x's that are undefined. But my range does have some undefined values. So my range starts at negative 3 and goes up, but the negative 3 is not included, and then it goes up towards positive infinity. Okay? So even though these values are getting really, really close to the negative 3, they're never going to quite get there, which is why it's not included, and then they'll go up to positive infinity. Okay? All right. So now I'm going to take a little break, and we're going to talk about interest, and then we'll talk about simple and compound interest. So interest is what you pay when you borrow money. And there's 2 types of interest. There's simple interest and compound interest. So let's talk about simple interest first. Okay? The formula for simple interest is that the interest is equal to the principal times the rate times the time. Okay? Simple interest usually is on your big ticket items. Like if you're going to buy a car or a house or a boat, anything that costs a bigger sum of money, it's usually simple interest. If you have a savings account in a bank, oftentimes it is simple interest. Okay? So the interest, the I, is how much the bank makes by allowing you to borrow money. The P is the principal, and that is, say, what the boat cost or what your car cost. The R is the interest rate on a yearly basis. So if I'm paying 5% interest, that means that once a year they charge me 5%, or they give me 5% interest or charge. And then T is time, and the time is always in terms of years when we're talking about interest. Okay? All right, so I want to show you a simple little example using simple interest. So the median, remember that median is the middle. House price in Flagstaff for the year 2014 was $310,500. That's why they call Flagstaff poverty with a view. Okay? So let's say I want to buy that house, and my interest rate is going to be 4% once a year, and we usually finance a house for 30 years. Okay, so it's called a 30-year note. All right. So before I figure out my house payments, the first thing that I do is I want to calculate how much interest is accrued over that 30 years. So my interest is equal to principal, rate, and time. My principal was how much the house cost, which was $310,500. My interest rate was 0.04. We always do the interest in decimal form, and then I'm going to multiply that by 30 years. So when I do that math, you find that the interest on the house, the money that you pay to the bank to loan you money, is $372,600. Oops, that's $600. So if you'll notice, you actually pay more to the bank than what the house is worth. So on a 30-year note, the cost of the house doubles. So now let's say I want to figure out what my monthly payments are going to be. So I add my original cost of the house, add the interest that I'm going to pay over the course of 30 years to get a sum of $683,100. So that's what the actual cost of the house is based on the interest, okay? And then I'm going to divide that by 30 years, and there are 12 months in a year. Okay, so I'm going to do the 683,100 divided by 360, and it turns out that your house payment every month is $1,897.50. That is an expensive house payment. So that's what happens when interest is calculated once a year. Okay, and let's say you were going to buy a house. All right, so that's kind of a rude life awakening. So now let's talk about compound interest. And a great example of compound interest are your credit cards. Okay, so I'm not earning, I'm actually paying money to someone else for the privilege of putting my purchase on a credit card. So I'm going to run through an example with you because I think that will help explain what compound interest actually does. So we are going to buy an iPhone, and our iPhone is going to cost $500, okay? And we're going to purchase our iPhone on our credit card. Because we're young, our interest rate on our credit card is going to be 30% compounded monthly. Okay. All right. So we're going to take our $500 purchase, and we're going to have to pay tax on it, sales tax. I guess I'll qualify that. And our sales tax in Flagstaff is 9.778%, or at least it was at one point. Okay. And then each month we're going to make a minimum payment of 10%. So oftentimes when you get your credit card bill, which is the sum total of all of your purchases plus the sales tax, you can make a 10% payment on your credit card. So if I take my phone that we bought at $500, multiply it by 1.09778, okay, I can explain why it's 1 plus the percentage later. I know that the tax or the cost of my iPhone is actually $548.89, okay? So in month 1, okay, I've now spent $548.89, okay? And I'm going to pay the 10%, okay, which means I'm going to pay, and I'm going to round it up a little bit, I'm going to pay $55, okay? Which means that the balance that I didn't pay, or what's left on my credit card, is $493.89, okay? And so let's assume that I make no other purchases and that's the only thing on my credit card, which is not realistic, but let's assume that's what people do, or what you're going to do. So the second month rolls around, so I haven't made any new purchases, but now they take my previous balance of $498.89, multiply it by 1.30, which is the initial amount plus the 30%, and now in the second month I owe $642.06. But the stupid iPhone only cost $500. I've already I paid tax and I made a payment on it, and instead of decreasing my bill is going up. Okay, so I'm going to go to my next page. Okay, so I'm going to make a payment in month 2 of 10%. So I'm going to pay $65, this time a little bit more than 10%. Okay, so my bill, when it came, was $642.06. I'm going to pay $65. So the balance at the end of month 2 is $577.06. Okay? All right, so that's after 2 months. So the amount that I owe is still going higher. Let's do one more month. Okay? So in month 3, sorry, now I'll do my colon. Okay? I owe the 577.06. I multiply that by my 30% interest rate, and I get 750.18. By including the 1, it adds the 30% of this right back to that initial value. So I'm going to make my minimum payment, which is 10%, and I'm going to pay $75, which is a little bit less technically than 10%. And the balance now at the end of the 3rd month is going to be $675.18. So you can see by making that minimum 10% payment, I'm really not making any headway on how much I owe. The cost actually keeps going up. Okay? So that is a fascinating process, and that is what compound interest does. So the interest is added to the initial amount, and then the interest is calculated, and that's why compound interest grows so quickly. All right, so now let's talk about the formula for compound interest. So it's going to be A is equal to the principal. A is the amount in the bank. P is the principal times 1 plus the interest rate divided by the number of compounding periods raised to the NT. Okay, so I'm going to write all those out for you. A is the amount, either in the bank, in your wallet, whatever. I just tend to think of it as in the bank, or how much you owe. P is always your principal, and that is what you pay for the item, or if you're making an investment. R is your interest rate, and our interest rates are always used in decimal form. So remember, I divide by 100, so I move the decimal place 2 spots to the left. N is the number of compounding periods per year. So for example, if I'm compounding monthly, then my number of compounding periods is 12, because there's 12 months in a year. If I'm compounding quarterly, there are 4 quarters in a year. If I'm compounding semi-annually, I'm compounding my interest twice a year. I could also compound my interest daily, which is what some of the quick loan places do, which is legal extortion, and your compounded period would be 365. My T is for time, and we always want time to be in years when we're talking about money. Okay? All right, so now let's do an example, and then I'll show you how this works in your calculator. Okay? All right, so I'm going to deposit $4,000 in an account. Okay, it's going to pay 2.92% annual interest. Okay, and then I want to find the balance after 1 year if my compounding periods are different. So if it is compounded quarterly, B is going to be daily. Okay, so I'm going to either compound it quarterly or I'm going to compound it daily. Okay, so let me write all of our given information down. My formula is A is equal to P times 1 plus R divided by N raised to the NT. My principal was $4,000. Okay, My interest rate is 0.0292, okay? I'm going to compound the first one quarterly, so this is going to be A. And I want to do it for 4 times 1, because I'm going to do it for 1 year. So let me show you how I would enter that in my calculator, okay? You never want to do this math first, because if you do, it will generate a significant error because we're raising things to a power. So I would enter my 4,000. Let me put it over here, maybe it'll be easier to see, okay? See, there you go. And then I'm going to put parentheses, 1 plus 0.0292 divided by 4 raised. And then I really don't have to do the parentheses, but I'm just going to show you so we get in the habit. Remember, on some of our calculators, when we raise something to a power, we need to put it in parentheses. And it tells you that at the end of 1 year, compounding quarterly, my amount in the bank is going to be 418.085. Okay? Grew pretty quick. That's in 1 year's time, so it gained $118 in a year. The second one was if it's compounding daily. So again, it's the same formula, 1 plus r divided by n raised to the nt. Okay? My principal's still the same. It's still the $4,000. My interest rate is the same. The only thing that changed was my compounding periods, and I'm going to raise it to the 365 times 1. Okay? Alrighty? Okay, and then when I do that, I'm going to end up with, when I do that math in my calculator, let me put it right here so you can see it. Okay? So I'm going to do 4,000 times 1 plus 0.0292 divided by 365 raised to the 365 times 1, and I get that compounding my interest daily is not significantly more. Okay? Alrighty. But what happens then if I were to change the number of years, then that value would get larger and larger significantly. Alright? The reason that credit card debt is outrageous in our country is A, we don't pay off our bills at the end of each month, and B, it's drawing an interest rate of 30% compounded monthly. So that is a significant issue. Alright, so I'm going to give you your problems. So we're done with our first lecture for the new year. Woohoo! Okay, number 1, I want you to sketch, except I can't spell, sketch the graph. So I would recommend that you put the graph in your grapher, graph it, okay, and then find the important points, labeling the important points. On the important points for an exponential function, you need to label the y-intercept. And remember, you can do that on your calculator by doing second and then calculate, and then you want to find a value, and then you enter x is equal to 0, because that's the value of x for the y-intercept, and then the calculator will tell you what the y-intercept is. Okay? Then I want you to describe the transformations. Okay, just like we've done in previous. So your first one is y is equal to 5 times 4 raised to the x plus 2. And your second is y is equal to a negative 3 times 4 raised to the x minus 1 minus 2. So I don't think I've stated this already, but I just thought of it. You cannot do the 5 times the 4 and then raise it to the x. You always have to do, if you remember your PEMDAS, parentheses, exponent, multiply, divide, add, and subtract. So I always have to do this first, then I can multiply by the 5. So you can never simplify these equations by multiplying the 5 and the 4 or the negative 3 and the 4. Okay? All right. And then your next problem is you are going to purchase an antique table, because I'm sure that's what you want to run out and purchase, for $450. Okay? The value of the table increases 6% each year. Okay? And then it says write an exponential growth model. Remember that B is your growth rate, and it's going to be 1 plus the percent. Okay? And then predict, which means you need to substitute in a value, the value of the table in 10 years. Okay? So this is, they want you to write this model, A, B to the X. We're not doing compound interest. Okay? All right. Your next problem says you invest $3,000 in a savings account. Okay, because you can't see it. All right, now there's your investment. Okay. All righty. Oh, I'm sorry. This one says, guess I should read before I write, you want to have $3,000 in your savings account after 3 years. Okay. It says find the amount you should deposit so you're looking for P for each situation. Okay. All right, and let me give you the situation. So it says you want to have $3,000 in a savings account after 3 years. Find the amount you should deposit. You're looking for P for each situation. So here are your situations. So A, the account pays 2.25% annual interest compounded quarterly. So in the equation that you're going to use, N is going to equal 4, and your R is going to be 0.0225. Okay? And in this one, you're looking to solve for P, so you have to solve the equation for P. Okay? And then the next one is the account pays 3.5% annual interest, which is just the way that we talk about interest, compounded monthly. Okay, so in this particular problem, your compounding periods are 12. There's 12 months in a year, and your rate is going to be 0.035. Okay, and again, in both of these, you're solving for P. Okay, alrighty. Good luck on your problems, and I will see you tomorrow.